Welcome. In the next few minutes, we will demystify backpropagation, the single algorithm that powers almost every modern neural network, from image recognition to language models to self-driving cars. We will cover the history, the mathematics, a fully worked numerical example, and a real-world classification problem. A little history first. The mathematical idea behind backpropagation, the chain rule of calculus, is centuries old. Gradient descent itself was described by Cauchy in 1847, but the modern formulation, reverse-mode automatic differentiation, was published by Seppo Linnainmaa in 1970. It was Rumelhart, Hinton, and Williams in 1986 who popularized it for training neural networks. In 2012, AlexNet showed the world that with enough data and compute, backpropagation could change everything. By 2017, transformers extended its reach to language. And in 2024, Geoffrey Hinton received the Nobel Prize in Physics, in part for this very work. A neural network is just a stack of layers of neurons. Each neuron receives numbers from the previous layer, multiplies them by weights, adds a bias, and passes the result through a non-linear activation function. Information flows from the input layer, through one or more hidden layers, to the output layer. Focus on a single neuron. Its output is computed in two steps. First, a weighted sum. Z equals the sum over I of Wi times Xi plus a bias. Then an activation function, like the sigmoid or ReLU, is applied, producing the neuron's output A. In the forward pass, data flows from left to right. We start with the input vector X, which becomes the activation of layer 0. For each layer L, we compute ZL, the linear combination of the previous activations using the weight matrix WL and bias BL. Then we apply the activation function sigma to get AL. After the final layer capital L, we get our prediction Y hat. Watch the signal propagate forward through the network. Let us make this concrete with real numbers. Consider a tiny network, one input, one hidden neuron, one output. Input X equals 1. The first weight W1 is 0.5 with bias 0.1. The second weight W2 is 0.8 with bias negative 0.3. Our target output Y is 1, and we use the sigmoid activation. Forward pass, Z1 equals 0.5 times 1, plus 0.1, which is 0.6. Apply sigmoid, a 1 is approximately 0.646. Z2 equals 0.8 times 0.646, minus 0.3, approximately 0.217. Sigmoid again gives Y hat, approximately 0.554. The squared error loss is about 0.1. Our prediction is too low, we wanted 1, we got 0.554. Now the backward pass. Delta 2 is Y hat minus Y, times the derivative of sigmoid, approximately negative 0.11. The gradient with respect to W2 equals delta 2 times a 1, approximately negative 0.07. Propagating back through W2, delta 1 is about negative 0.02. Since X equals 1, the gradient with respect to W1 is also about negative 0.02. These gradients tell us exactly how much, and in which direction, to nudge each weight to reduce the loss. More generally, the loss function L is a single number measuring how wrong the prediction is. For regression, we often use the squared error. For classification, we typically use cross-entropy. Either way, our goal is the same. Minimize this number by adjusting every weight and bias in the network. To minimize the loss, we need to know how a tiny change in every weight affects the loss. This is a problem about derivatives, specifically the chain rule. The chain rule tells us that the derivative of f with respect to x equals the derivative of f with respect to g times the derivative of g with respect to x. For example, the derivative of sine of x squared is cosine of x squared times 2x. Backpropagation is nothing more than the chain rule, applied systematically to the computation graph of a neural network. Generalizing what we did by hand, there are 4 key equations of backpropagation. First, the error at the output layer. Delta L equals the gradient of the loss with respect to the activations, element y's multiplied by sigma prime of ZL. Second, propagate the error backwards. Delta L equals W transpose from layer L plus 1 times delta L plus 1, again element y's with sigma prime of ZL. Third, the gradient with respect to each bias is simply the delta at that neuron. And fourth, the gradient with respect to each weight is the input activation from the previous layer, times the delta at the receiving neuron. Visually, the error signal flows from right to left, through the very same connections that carried the input forward, but now in reverse. To visualize what gradient descent is actually doing, think of the loss as a landscape in many dimensions. Here is a simplified two-dimensional version. The height is the loss. The floor is the space of all possible weight values. Training is the process of rolling a ball downhill on the surface. Each step of backpropagation tells the ball which direction is steepest, and the learning rate decides how big a step to take. Notice how the ball naturally settles into the minimum at the center. With every gradient in hand, we update each weight using gradient descent. The new weight equals the old weight, minus eta, the learning rate, times the gradient. The same rule applies to the biases. Using our earlier example with learning rate 1/2, W1 becomes approximately 0.510. W2 becomes approximately 0.836. Both weights moved in the direction that reduces the loss. Let us see backpropagation solve a real problem. The classic MNIST task, recognizing handwritten digits. On the left we have an input image, 28 by 28 pixels, 784 numbers in total. In the middle, a neural network with two hidden layers, 128 and 64 neurons, ending in 10 output neurons, one per digit. On the right, the network's prediction, a probability for each digit from 0 to 9. Training this network with backpropagation on 60,000 examples takes only a few minutes on a modern GPU and reaches over 98% accuracy. So what does training actually look like over time? Here is a typical learning curve. The x-axis is training epochs, one full pass through the data. The y-axis is the loss. At epoch 0, the network is initialized randomly and its predictions are essentially noise. As backpropagation repeatedly nudges the weights downhill, the loss drops sharply at first, then more slowly. Eventually it flattens out, the network has converged. This shape, exponential decay to a plateau, is the signature of a healthy training run. Backpropagation is powerful, but it is not magic. Gradients can vanish in very deep networks, they can explode in recurrent ones, the loss surface is riddled with local minima and saddle points, and the whole process is computationally expensive. Despite all of this, backpropagation made the modern AI revolution possible. From ImageNet to speech recognition, to machine translation, to large language models, to AlphaFold predicting the three-dimensional structure of every known protein, all of it is trained with backpropagation. To summarize, forward pass, compute the prediction. Compute the loss, measure the error. Backward pass, use the chain rule to get every gradient. Finally, update every parameter with a gradient descent step. Repeat millions of times and you have a trained neural network that, in essence, is backpropagation. Thanks for watching.